what you need. So this has absolutely no sense for me, but maybe for you, I don't know. This also means that if you know op cache poisoning and VLAN hopping, you can poison a cache with a double VLAN encapsulation. If you know VoIP decoding and .11 and web, you can decode a web encrypted .11 VoIP capture. If you know HITBSecConf2006 and crossroute, you can crossroute to VPN concentrators. You can combine everything. Then the concept of probe once, interpret many. This is a big difference with other tools. When you do a probe, you will send many packets and you get a raw result. The result is a list of stimulus-response couples and a list of unreplied stimuli. And this has not been interpreted. This is only decoded packets from the network. It's very raw. And then, when you have it, you can interpret it or represent it the way you want, and do it again and again without needing a new probe, so that you can refine interpretation without probing again and again. For example, if you do a TCP scan, you have a TCP reset packet saying the port is closed, and you say, oh, maybe it's not it, but the router behind it that sent it. You can check the TTL without doing a new probe. So this is a figure of how it works. You build an implicit packet that's worth many packets. For example, for a scan, you give it the function that will make a list of it, send all the stimuli, get some responses. It will match the stimuli received with the response received with the stimuli you send. And when you find a match, you make a couple, and at the end it returns you a list of couples, stimulus, response. And then it returns you a list of unanswered packets. Okay, now we'll see a quick overview. So this is the prompt. You can, doing like this, you will instantiate an IP layer with TTL set to 10. So you can look what is in the variable. This is IP, TTL is 10. Other fields that are default value are not shown. But they are still there. For example, the source is localhost. If I change the destination, you will see appear here, and you will see the source I've been changed according to my routing tables. If I delete an attribute, it will go back to the default value. So we said it was 10, and now it disappeared, and now it's 64, default value. We can stack upon a TCP layer, and we get IP TCP, a TCP IP packet. We can spell some methods from the instance. For example, the command method will return you a string that you have to type to get the packet. For example, you have the show method that will show you a very detailed view of the packet, so that you can get every value of the fields. And we can see, for example, the default value there. So you can see the packet, very detailed view of the packet. When you stack many protocols, you can access to all the layers using payload. So for example, pkt.payload.payload.checksum could access a UDP checksum if you have an Ethernet packet with VLAN encapsulation. You can use some items, but it's not always a good syntax, because if you don't have Ethernet anymore, it's not working. So if you use this syntax using this item, packet square bracket layer, it will return the ASCII layer. You can test for the presence of a layer using a layer in packet. And this is a special case, for example, when you have IP on IP. If you want the second IP layer, you will use colon 2. An example, if UDP in PKT print PKT square bracket UDP.checksum, will print the UDP checksum of the packet if it is present. And what's cool with this code is that it's totally independent from the lower layers. If it comes from a PPP link, if it comes from a web capture with .12 encapsulation or whatever, you don't mind about it. If there is an UDP layer in it, it will find it and bring it to you. Other stuff is about building and dissecting. If you use the str function to a string applied to your packet, you will get your TCP IP packet as a string. And if you instantiate an IP layer with underscore in Python, means it's the latest result. So IP applied to this string will dissect the string. So it will find all the fields of IP, and then the remaining of the string will be given to TCP because IP knows that the protocol must be TCP. So the full packet is correctly decoded. Then we also can change some stuff. We will put in the TTL, instead of 64, the default value, we'll put 10 to 14. This means all the value 10, 11, 12, 13, 14. In the TCP destination port, we will put 2 ports, 80 and 443. And then B becomes an implicit packet that is worth 5 times 2 equals 10 packets. If I iterate over it, I will get the 10 different possible values from the Cartesian product. So just doing this, you can design a list of packets very easily. There are other methods, for example, the PS dump or PDF dump that will give you a very an exploded view of the packet, and you can see the way it is assembled. This is very cool to put into a report if you found a packet of crash box. It's cool to see how a packet is disassembled, or if you need to teach some network stuff. Another method is the sprintf method. You give it a format string, and it will replace it with value from the packet. For example, this format string, this is a formatting directive, and it will be replaced by the IP source, very easy. So if it's applied to this packet, you will get this string, the sources, and the real IP taken from the packet. Now, we have seen how to manipulate packet. Let's see how to send them. It's very easy. If you remember, B is an implicit packet that is worth 10 packets. If I send it, I will send 10 packets. That's easy. You can send in 3 times. You can also provide some parameters like the time interval between 2 packets, the fact you want to send them in loop, and you have to type Ctrl+C to stop it. You can also use the sendP function to send at layer 2. This one works at layer 3, use the routing tables. This one works at layer 2, working at the Ethernet level for Ethernet interface, for example. And this will send the string row on the Ethernet card. And if you disable it, you will see something that has no sense, but you can speak directly on the Ethernet level. Other example of the power of the expressiveness of SCABI. This is the Microsoft IP option denial of service proof of concept, which was 115 lines of C code without comments. This is the same with SCABI. It's only 1 line, and everything is concentrated, so you can see what it is exactly. Same, for example, for the TCP dump, easy script, remote denial of service. The exploit was 225 lines, and this is the same with SCABI. So you have everything, you know it's gray, you know the protocol is 254. This is the string I ripped from the exploit, so it's only 1 line, and you have all the information you need to understand exactly what happens. You don't have to search into 250 lines of C code. I feel a bit sad about the people that write all those lines to do only that. Other fun stuff is the fuzzing. This is done using the fuzz function so that you can make a packet become fuzzy. In fact, it will replace the default values by random values, except those that need to be calculated like checksum. So you can send very strange packets that looks like corrupted, but the checksum will be correct. For example, or the length will be correct. If you want the length or the checksum to be incorrect, you have to tell them to be random, like we did for the version. Here we forced the version should have been randomized, but we forced it to be 4. And as the contrary, we could have forced the UDP checksum to be random there, but we did not specify anything, so it will be calculated. And then you can send your packet in loop, and it will send, it will fuzz the NTP layer. We can also use fuzzing. This was constructive fuzzing. And we can also use fuzzing by iterating something. So we will either use the corrupt byte or corrupt bits function that will be able to corrupt a given amount, given percentage of a string. either by random bytes or by flipping bits. You can use either, for example, you capture a payload, and then you reset it many times, but corrupted. The UDP checksum will be calculated, so it will look like it is okay. Or you can use the function as a post transformation. So here we construct an NTP packet, and then we corrupt it right after building it. You can also sniff packets. So this is, I will sniff 5 packets with a BPF filter of TCP. I will get this object. This is a list that give you some statistics and that hold your 5 packets. You can also use PRN with a callback that will be applied to each packet captured, and that will print for each packet its summary. So you will get something like this, like a TCP NAT. You can apply the summary function to the summary method to a list, and you will get what inside the list. You can write it to pickup file, read it, and everything is still there. We can also have some nice stuff with pre-printing. So we printed the summary, but we also can use sprintf to use our own summary. So this is what we could get sniffing with printing exactly what we want. We can also do smarter stuff using, for example, the signal strength of stuff. This I can demo it now. Should be. It should work. So this is, for example, what you can use with sniff and the sprintf function. So it's nothing magic. I just use the signal I get from my Etheros card and multiply it by a string, and it's only a matter of assembling the stuff correctly. I can also, from a list, get all the conversation between layers. So if I do, I'll read some stuff. And this is the conversations I've seen in the first 100 packet of my capture. So you see, it's very easy to do. You can use PS now to get a PS or a PDF. Each page is a packet, and you can manipulate it like a list. This one I will be very fast. You can also use the make table function that will transform your list into a table, a two-dimensional table. You just have to provide what you want in the column header, what you want in the row headers, and what you want inside the cells. Here we want the destination of the stimulus here, the destination port of the stimulus here, and this from the response inside the cells. So we get either the TCP flag if it's TCP, or the ICMP type if it's ICMP. So you see in 2 lines we have a better scanner than Nmap that is more precise. This is how to send and receive. So we've seen it's a SR1 function that will give you the first answer to your stimulus. So if this is a ping, we get the echo reply. You see there is a padding, we don't miss it. And if you compare to HPing where we missed the padding, here we can see there is data leaking and we can investigate it. Other nice stuff is about the plotting stuff. I will try to gather many IPIE from a target and then plot them. And if there are many boxes behind it and the IPD is incremental, I will be able to count it very easily. So this was Yahoo.fr, 6 machines. Here are some more that I got. Apple is very funny as usual. Google randomized, kernel 0. Microsoft, there are only 1 machine because it depends on the way they do their load balancing. And this is Yahoo.fr, I think it's 2 or 3 months later, 8 machines. So they brought 2 machines. We can do also traffic estimation if we have only 1 machine, and we can isolate 1 machine. So using the dplot, you will have an estimation of the traffic of the packet sent by the IP stack. We can also try to do a round trip time estimation at just doing this. This will